Welcome to the pre-recording of the second half of lecture 19, scheduled for the middle of week 7 in our 8-week summer course on computer algorithms. So in this lecture, we're going to deal with showing how a problem is NP-complete. So this is the middle of week 7. It's also getting in the middle of the last chapter that we will cover in this course. So in some sense, this is one of the more important lectures in the last half of this last part of this course. Okay, so we will deal with circuits, but let's first, to keep this lecture as self-contained as possible, recapitulate the most essential definitions up to this point. For most of this course, we dealt with algorithms which had a worst case running time that was bounded by a polynomial in the input size. We call such algorithms efficient, and all problems for which we know an efficient algorithm, all such problems is the collection P of polynomial time problems. Although polynomial time is a property of an algorithm, we actually consider P as a collection of problems that can be solved efficiently. Now, the class NP is the class of all problems for which we know an efficient certifier. So given an output to the solution, we have an efficient algorithm to check whether that output really solves the problem. So there is an important but subtle distinction. So we replace in the definition for NP the word algorithm by certifier. Now, previously we have shown that if a problem for which there is an efficient certifier belongs to the class NP. Now, if we have an NP complete problem, so these are problems in the class NP, in the set NP, if such NP complete problem would be solvable in polynomial time, or if that is solvable in polynomial time, then it would mean that both sets P and NP would be the same. That's still an open problem. Most people, and including me and many important people, believe that this is not the same. But still, we don't know. So showing that something is incomplete is a lot harder than showing whether a problem is in the set NP. So that's actually the important question and the important problem that we're going to deal with in this lecture. In the previous lecture, we have shown that if you have an efficient algorithm to verify that the output is a solution to the problem, then actually the problem is in NP. And all problems in the set P are automatically in the set NP as well. Okay, so let us introduce circuits. So a circuit, here we see an example of a circuit. So there are inputs. So the inputs can be variables, x, y, and z, and they can also be constants. So we read this circuit either as a logical expression with ands, ors, and the negation, Or we can also make a picture out of this, where we read this from bottom to top. So we have at the bottom our constants as special input gates. And then we have the three variables x, y, and z. The internal nodes are the logical gates, are the operation, the or, the and. The ors and the and, they take in two inputs, so they have two arrows leading into their nodes. The negation is a unary operator, so takes only one node. Here you should read this not as it is the not of 1 and x. So there are multiple inputs, but there is only one output. So all the way on top, we have the node which will be the final operation that is performed, and that is the AND operation here in this example. So this is an example of a circuit. So one can see that every logical expression with not and or, and where the variables represent true and false statements, so the 0 is false, the 1 is true, that every such logical expression can be translated into a circuit, and the other way around, every circuit we can make a drawing of it. Okay, so here is then the definition of a circuit. A circuit is a labeled directed acyclic graph. Acyclic means that there are no cycles in there, so you go in one direction. The sources are the inputs, and a node in a directed graph is a source if there are no incoming edges. So we have two sources, two types of sources. Either we have constants, 0 or 1, or we have variable names. So those variable names are called the inputs. Then we have internal nodes, which are the three Boolean operations, the not, the or the and, also called disjunction, conjunction. We have binary operations, so every node which is or and has two edges coming in. The negation is unary. So we have multiple sources typically, which multiple inputs, but we have only one output in the language of directed acyclic graphs, where we are having one sink. You could also see that the information flows from the inputs upwards to the, or actually downwards if you think about fluid flows. It goes into the sink, which is the output. And the output actually returns what the circuit computes. Okay, why is that now important? Well, we will consider the circuit satisfiability problem. Remember again our problem, we want to show that any given problem, a new problem, that this is an NP-complete problem. So how can we show that there are problems? If you know a polynomial time algorithm for such problems, then you can solve any problem for which there is an efficient certifier. Okay, so we have the circuit satisfiability problem. If we have given a circuit, then we say that that circuit is satisfiable if there is one input, can be also be more, if that for the inputs, for that one input, the output equals 1. So then the problem, so we are formulating our problems as decision problems. So for any given circuit, is there an input for which the output is 1? So given a circuit, decide whether K is satisfiable or what, or not. And if you can solve that problem in polynomial time, then the set P equals NP. So circuit satisfiability is NP complete. So that will be the main theorem that we will be proving in the second half of this lecture. But let's first dwell a little bit on the role of circuits. So here is a problem, again formulated in a graph. Given on input a graph with vertices and edges. Does this graph contain a two-node independent set? What that means is that is there a set consists of two vertices for which there is no edge in between. It's a very simple problem, but we will translate this problem into a circuit. And the problem is chosen to be simple for we should be able to draw the circuit. Okay, how are we going to define this problem as a circuit? Well, what is the input? The input consists of all possible choices of two elements of the vertex set. So for any two vertices that we pick, we have to be able to decide whether there is an edge or not. So we will have a sequence of bits. So you label the vertices and the pairs of vertices will correspond to a 0 or a 1 in a very long sequence of bits. But again, it is you can store this edge representation in quadratic space-time. Then a certificate will actually tell you, will actually give you an assignment, will actually present a selection of the vertex set where so it's some sequence of n bits and there is a 1 at position 3 if you select vertex 3. Otherwise there will be a 0. Okay, in a 3-node graph, you can write down, or we can draw down the circuit which answers this question. So this is a certifier that given a selection of an independent set gives you 1 if that selection is indeed independent set. So if there is, in other words, if that it's essentially also a lookup in a long string. That's also what this problem is. So let's read this circuit. We have 6 nodes at the bottom. We have 3 constants, and the 3 constants are encoding whether there is an edge or not. So we have 3 nodes, U, V, and W. These will be the 3 inputs. When we have an input 1, we say that we select that node. If we have an input 0, we do not select that node. So for any possible pairs that you pick, the circuit will tell you 1 or no, 1 or 0, if there is an edge between these two vertices. So there are 2 parts. You have to pick at least 2 nodes, UV, UW, or VW. So these are the conjunctions here, the ands. Then the ors will, so the right-hand side of this big logical expression of what the circuit computes will be 1 if you have at least 2 ones for a U, a V, or a V and a W. And then you select this, you combine this selection whether there is an edge or not. So these are also conjunctions. So for any pair, you check whether there is an edge or not. You do the OR, and actually you negate everything. So you must have at least one pair for which there is no edge. And that tells you that you have a two-node independent set. Just to verify here, this is the problem we just solved. I know it's a simple problem, but the slide was just long enough to draw this entire circuit. So we have U and W are the two-node independent set. So if you select U and W, so you give an input 1 for U and W, then you see that at the right side of the circuit there will be one, the middle one, U and W will be 1, and that will be sufficient to make this entire right side of the circuit make it 1. And then you also select U and W, and there is no edge between U and W, so that constant is 0. It will actually, the fact that you do not select, so here actually I should have been more complete. So here it actually does matter that you do not select V, so V equals 0 should have been specified. Let me uh, clarify this. So if you have V equals 0, then all these other ones are 0. But the fact that you have this already makes it 1. And negating 1 actually, I'm sorry, so you have here, you have a 1 because of the other ones. You negate, so you have a 1. So you have a 1 and a 1. Okay, I hope I didn't mess this up too badly, that it should be clear that you can encode the certifier for verifying that indeed this problem has two nodes for which there is no edge, that you can encode this as a circuit. Okay, so now is the main theorem. Circuit satisfiability is NP-complete. So what do we need to do for that? We need to do we need to show a lot more than that this problem is actually that this has an efficient certifier. We need to there are three stages in the proof. Any algorithm can be written as a circuit. That's the first part in the proof. The second part is that for any problem, we actually have an efficient certifier. And then we call the black box solver. So to solve the circuit satisfiability. So that means that for any problem, we can actually reduce it in polynomial time to the circuit satisfiability problem because of these three steps. So let's look at the first step. Any algorithm can actually be formulated as a circuit. Notice that our algorithms are outputting yes or no. So that's also the output of a circuit. This is already very convenient. We take on input also n bits, a sequence of bits. So n can be any number, but it should be finite. So that's the input. Now, indeed, so the input bits are the input nodes, and the output, yes or no, is actually the outcome of the algorithm. So our algorithms have one sink and multiple sources. So if the algorithm that we have takes a polynomial a polynomial number of steps, polynomial in the input size, then also our circuit will need to have polynomial size. And then all the computational steps on a real computer they work on bits, so we're talking here about real computers, and the primitive operations are realized by logic gates, by the AND, the OR, and the NOT gates. Step one in the algorithm, so any algorithm, step one in the proof, any algorithm can be formulated as a circuit. Okay, so we can then write the certifier algorithm as a circuit. What does it mean to belong to the set NP? Well, we have an efficient certifier. So we have an algorithm which has a worst case running time that is bounded by a polynomial size in the input. Size in the input and size also as the certificate. Okay, now what do we actually need to prove? We need to prove that any problem can be reduced to the circuit satisfiability. So again, what does it mean to have an algorithm that solves a problem? It means that you decide that you have an input that returns yes. So deciding whether for an input S it belongs to the problem set means that for that input the solution to the problem is yes. Okay, so we have a black box solver for the circuit satisfiability problem. And we will call this black box solver as follows. Our certifier that we have for the problem X, it belongs in NP. It's an efficient algorithm. Therefore, we can formulate it as a circuit. And the size of that circuit will be polynomial time in the input nodes, and the size of the certificate. Now, what does it mean again for a problem to be belonging to that set X? It means that there is a way to actually, if there is an algorithm that gives you output 1, and that is now equivalent for the circuit K to be satisfiable. So any arbitrary problem for which we do have an efficient certifier, we can reduce it in polynomial time to the circuit satisfiability problem. And we don't really know what the black box is for our circuit satisfiability, but the main point is that every arbitrary problem can be reduced in polynomial time to the circuit satisfiability problem. That just means that the circuit satisfiability problem is NP complete. And that is the end of the proof of our main theorem. So the main theorem essentially of this last part of the course. So this is important. In what follows, we will consider applications of this theorem. Remember the transitivity. So here is a proposition which essentially is an application of the transitivity property that we derived in the last lecture. In the last lecture, we said that if z can be reduced in polynomial time to y, and y can be reduced in polynomial time to x, then z reduces in polynomial time to x. Well, we have the same thing here. If we have an NP-complete problem, and we can, for a new problem, which is an NP, we can deduce that NP-complete problem can be reformulated in polynomial time to that new problem, then actually also that new problem is NP complete. So this is a very important property. So let's prove it. The proof is important always to make us reflect on why it is true. And so let's go through the proof. So we need, if X is in NP, so what we need to do to prove that X is NP complete, every problem for which we have an efficient certifier can be reduced to that problem that is NP complete. So because we have a NP complete problem Y, then we can reduce that problem, any NP problem Z, to that problem Y, given that Y can be in polynomial time be reformulated into X, and we have the transitivity property of the polynomial time reducibility. That actually means that the problem Z, any problem Z that is in the set NP, can be reduced to X. So therefore we have that X is NP complete. If you have an efficient algorithm for X, then you have an efficient algorithm for all problems in the set NP. And there is no more a distinction between P equals NP. Okay, so there are many more problems that are NP complete. Let us look at to the tree satisfiability problem. So what is the tree satisfiability problem again? So we have a sequence of clauses. Every clause consists of three terms, where a term is either a Boolean variable or the negation of a Boolean variable. We have a set of k clauses, and we ask, is there an assignment of our Boolean variables such that all the clauses are true? So the conjunction of all these clauses of exactly three terms are true. Here you see an example that we have used previously. So we have three clauses, each of three terms. Doesn't need to be that way. We can have k can be any number, but we see that it is satisfied by picking x equals 0, y equals x equal 1, y equals 0, or z, and z equals 0. So this is the satisfiability problem. We will show that this problem is also NP complete. How do we do this? So this is another important theorem, but we will use the main theorem already, that circuit satisfiability is NP complete. So first of all, if you start by saying that a problem is NP complete, you have to start by saying that it is in the set NP. We do have an efficient certifier. That's what we have already indicated in the first half of this lecture. Then if we can reduce to circuit satisfiability, then we will have that this tree satisfiability is NP complete. How do we do this? There is a more general problem of satisfiability called SAT. And we will start from a circuit. We will generate a sequence of clauses. Any general sequence of clauses can be reduced to a tree set. So we will reconstruct this into a tree set problem. Okay, so how do we do this? How can we convert any circuit to an instance of the satisfiability problem? Notice that the satisfiability problem had nodes that were either the uh, Boolean variables or their negation. So we actually don't have a negation operator in our sequence of logical expressions, only ands or ors. Okay, so with every node that is an input node, we will actually associate the variable. At the internal nodes, we have three different types of gates. So if we have a NOT gate, we will add clauses. So there is one node that enters. We will add the clauses at the node that enters with the NOT. We will add these two clauses. Verify that that expression is actually equivalent to taking the negation. So this is an extra exercise. It's the second exercise in this entire lecture. How could you do this? Well, you could set up the truth tables. So you have two different variables. You show that they are equivalent. We can also replace the OR operator at a node. So there are two nodes entering. We add the clauses, and the clauses are combined with the AND in the SAT formulation. Again, the exercise saying that this actually implements the OR operation can be done by truth tables. And for the AND operator, we are adding the clauses as listed here. And again, the next exercise, which you can verify, which you can solve with truth tables, are actually verifying that the rules here to translate the circuits into an instance of the satisfiability problem are actually correct. So they give you actually the equivalence between the two. Okay, so that's the first part in the proof. So the inputs now of the circuit for the, so we have input nodes in the circuit. So either we add the clause 1 or we add the negation if we have the value 0. So we need to have an output node which takes the value 1. So this gives you the output clause. Okay, then we have the lemma. So that what we have constructed from the circuit to the SAT instance is completely equivalent. So if the circuit is satisfiable, then also the SAT instance has a satisfying truth statement. If we have a satisfying truth statement, then also the circuit is satisfiable. Okay, so that's one thing. The next thing is that for any general SAT problem, we can actually construct a tree SAT, a tree satisfiability problem. We hinted at that in an earlier lecture, that actually the satisfiability problem is just as hard as the tree satisfiability problem. And how can you construct from any satisfiability problem a tree satisfiability problem? Well, if we have 4 variables, we can actually add variables and the clauses. And that actually can be used to replace terms. So if you have more terms, more than 3 terms, with extra variables, you can reduce them to clauses which have exactly three terms. So the construction is over here. So, what did we just do? We have proven that the circuit satisfiability problem can be reduced in polynomial time to an instance of the tree satisfiability problem. We can construct for a circuit a logical expression for which deciding whether the circuit is satisfiable, it is equivalent that the logical expression has a satisfying truth statement. The general logical expression can be reduced to a tree satisfiability problem. So we have this polynomial time satisfiability. So, and the tree set problem is our new problem, for which we want to show that that is incomplete, NP complete. Okay, so we have that the tree satisfiability problem is complete. And by the proposition, the transitivity proposition, so we could reduce the tree satisfiability to independent set, to vertex cover, to set cover. All these problems are now also NP complete. So these are all problems for which we have an efficient certifier, but we do not know an efficient algorithm. So no matter how you think about these problems, about designing efficient algorithms, if you can find one efficient algorithm for any of these problems here, then they are all NP complete. So the proof of the corollary here does not mention the set packing problem. For the set packing problem, you remember the exercise of the previous lecture that actually you need to solve here. So this is reflected in this as well. Okay, let me almost conclude with an exercise. So there is the strongly independent set problem. So the independent set problem asks, given a graph and a number k, is there an independent set of size k in the graph? So if there is a set of size k, that means that between any two numbers, there is no edge between any two edges, between any two vertices in the set. So there is no edge between them. So that is what it means to be an independent set. Now, strongly independent means that there is no connection of length 2 between any two vertices in that set. So that problem is NP complete. So the strongly independent set problem asks, given a graph and an integer k, is there a set of size k so that if you take any two vertices out of that set, there is no path of length 2. So you have to first prove that this problem is an NP. If somebody gives you a set of vertices, then you can verify efficiently that there is no um, path of length 2 between those two. And that seems to be straightforward. So if you have your graph representation, for every vertex, you can go to all the neighbors, and you go to all the neighbors of those neighbors. So think about the breadth first algorithm. You run it, but you stop after 2 steps. So at level 2, have you seen uh, the other point? So you can run this algorithm for all pairs. 2 steps, a constant number of steps. It depends on the degrees, it depends on the sizes. So that's an efficient algorithm. How can you now show that? So it is in NP, you have an efficient certifier. That's the first step. The second step is that you have to show that an NP-complete problem, you can reduce it to the strongly independent set problem. So you can start with the independent set problem and try to see that if you can reduce it to the strongly independent set problem. Um, so that is the task of this exercise. Um, go back to the definitions and show that this problem here can be in polynomial time reduced to the independent set problem, which is known to be NP-complete. You could also go back to the circuit satisfiability problem, but that's a much longer road. Okay, so here is then the general strategy, which is actually the solution strategy, what you should do to solve the previous exercise, to show that a new problem, such as a strongly independent set problem, is NP-complete. You have to show first that that problem belongs to the set NP. You do have an efficient certifier. You can verify with an efficient algorithm that a given solution, a given output is also actually solves the problem. Then choose a problem known to be NP-complete. It is best if you choose a problem which resembles the problem. And then you show that that problem can be reduced to your new problem in polynomial time. Okay, so that was the lecture. I hope that this did not confuse too much and that the main point of the lecture was clear. So the main theorem that we do have that we do have the circuit satisfiability as our first NP-complete problem. And with that, we could, by the transitivity, we could immediately create many more NP-complete problems.